Hello, everybody, and welcome to our DV Club today, where our focus is on Cocotb. Okay, we have 3 speakers today. But first of all, the attendees. We have over 227 attendees registered. And that represents 146 different companies in 39 different countries. So again, a very international audience and another popular event. As I said, we have 3 very good speakers today. The first one is Al Hakim Haider from Wartzilla. He's our first speaker. Then we have Philip Wagner, who's the FOSSI Foundation he works at FOSSI Foundation, but he's the person who wrote Cocotb. And then Grant Bowers of Garrison, who's a user of Cocotb. So it should be 3 very informative talks today. And again, a big thank you, first of all, to our sponsors who allow us to run these events. And they are Agnesis, Cadence, Synopsys, Brecker, and Tassolve, who host the events and allow me to do these free of charge for you. Okay, I'm going to stop sharing now, and we're going to hand over to our first speaker, and we'll do the introductions and make a start. Thank you.
Yeah, Haider, can you share your screen, please?
Yes, can you see my screen?
Yes, can you make it full screen?
Yes. Maybe the presentation.
Perfect. So I'll make the introduction and make a start. Our first speaker today is Haider Al-Kaim from Wartzilla in Finland. And he's an automation engineer there since 2017. His main interest areas are digital logic design, FPGAs, digital signal processing, wireless communication. Before that, he worked as a university researcher in the University of Vaasa, which is in Finland. He has BSc in electrical and electronics engineering and an MSc in telecommunication engineering. He's based in Finland, and the topic of his talk today is simple yet powerful open source HDL simulation with Cocotb. Okay, over to you, Haider.
Yes, thank you, Mike. Good afternoon. This presentation, I will try to argue that today, with all the advancements, the open source simulation tools for HDL has become powerful for serious work, yet they are still very simple to use for newcomers. Yeah, it seems. Sorry.
Yes, we are able to see.
I'm unable to switch. Okay, now I'm able to switch.
Yes.
Yeah. So the presentation will be split in 3 main sections. First, when and why is it a good choice to use Python for verification? And then an example of how you can integrate your own environment to simulate HDL with Python using only free and open source tools. And the third section will be a demonstration simulating a dot with Axelite bus. So it's not a trivial, but not too complicated example, which can show a test case. So I'll start first talking about why it's a good idea to use general purpose programming languages. If we look at a test bench, like in the right side, in VHDL, it's usually scripting the stimulus and verifying the results of the output. So it's different than the synthesis code. And the objective of verification is, of course, to verify that the implementation fulfills the requirements and specifications. Over the course of years, HDL languages like Verilog and System Verilog and VHDL have been augmented with more and more verification-oriented features, which are not synthesizable. However, in my opinion here, it's still more powerful and flexible to use a general purpose programming language for the verification part, like Python. The benefits that we would get, or some of the benefits, is that you don't need to understand the details of the implementation. So your reference for verification would be the documentation for requirements. And both the designer and verification engineer should be interpreting them the same way. And that way you avoid repeating the same mistakes. Also, the HDL will be tested by software, which is similar to the real use case when it will be the drivers and applications using the HDL. Now, why Python and Cocotb? I think we know that Python has very large, maybe the largest package libraries, and it's a very easy and friendly language and powerful. And by using Python, we have a large pool of talents to draw from. So we don't need people specialized in System Verilog or VHDL. And this opens the path to inviting the driver and application coders to join our verification effort. And why Cocotb is because when I searched about making verification with Python, Cocotb is the de facto methodology. And it gives you access to ports and the internal signals of your device under test. It has a very rich library with bus functional models in the Cocotb bus. We will show one today, which is the AXI. And it works with most simulators that are free and commercial. Unfortunately, Vivado isn't working yet. Hopefully that will be something in the future. But by using Cocotb, you also can migrate your verification to a different simulator with minimal modifications. Always there is benefits and potential drawbacks. One thing we wish we had there would be being able to see the test bench signals, but the Python test bench is running outside the simulator, so that's not visible. You can debug, or you can insert breakpoints in case of GHDL at least. Python is the very strong language, but it's still work in progress for one unified and powerful methodology like UVM. The performance will depend on case by case. It's complicated to benchmark the performance, but one case study shows that the execution time of UVM was much faster. A master CC is in Oulu here in Finland. However, this was never a bottleneck for our work, since all our simulations were finishing in few minutes. And you could, of course, accelerate certain parts by writing C extensions. And we have to remember that the most expensive cost is the development time, actually, and not necessarily the speed of the simulation. Here is an overview of, well, one suggestion of how your verification environment could look like. This is for VHDL. So the simulator is GHDL, which can generate trace files, which can be viewed by GTK Wave. But this could be Icarus Verilog, if you're using Cocotb, or Verilator, or any commercial simulator. The communication to the Cocotb is done through the VPI or VHPI with an additional wrapper that I'll show in the next slide. And the Python test will be written in Python and running through the Cocotb. On the code editing side, we use Visual Studio Code and Teros HDL running in WSL. And the reason that we opted for using WSL is that it's very convenient as you keep your Windows work laptops and all the files are easily accessible and the network and internet access is available. I'll skip quickly through this slide. It's details on how you can install these components shown in the previous picture. One thing about Cocotb is that maybe the main three repositories are the Cocotb itself, the Cocotb bus, which provides bus functional models, and the coverage model for functional coverage. Teros HDL is one-stop shop for many extensions that are handy in Visual Studio Code. Very powerful linting, even type checking, which I will try to demonstrate if time permits. So what is Cocotb? Quoting here, it's a coroutine-based co-simulation test bench environment for verifying the HDL and system Verilog RTL using Python. This picture here is famous if you have attended many presentations by now. The communication happens through the foreign language interfaces for Verilog VHDL or system Verilog, and there is this additional GPI on top of them. What do you get when you use Python? You get the full access to the internal signals and hierarchy of the device under test from Python. So not only the ports, which is quite powerful if you are writing assertions. Some basics of Cocotb here. First, how to run it. There is a very good webinar by Philip that you can find in this link. Basically, there's three ways to run it. Either by scripting your simulator or writing make files or the Python runner. When you script the simulator, you have the fine control over the simulation options, but you need extra work if you port to a different simulator. And the steps will go usually that you will compile as usual. So here are the HDL files. But then you need to export at minimum 2 environment variables pointing to your Python path for the test module and the name of the test module. Finally, when you run the simulator, you will need to pass the VPI switch and the location of the VPI shared library for your simulator for Cocotb. If you choose to run with make files, then it's similar here. You're exporting also path and sources. It's again explained in more details in the presentation by Philip. But we will demonstrate the example with the Python runner because it's the focus of the development now, and it allows you to leverage the power of Python to do a lot of things before and after the simulation. So some basics of the test bench. First, the DUT. So the DUT will be available to you from Cocotb. And it's an object that will give you the access to the signals and hierarchy with the dot operator. For example, here, dut.axi, reset n.value, and so on. Cocotb.test, when you import this decorator, it will turn your function into a test. And then this test will be picked automatically by the test runner. Any function that is annotated by the Cocotb test. Then you have normal definitions and async definitions. The async definitions will use a coroutine. So this is asynchronous. And maybe it's not exactly the same, but we can think of it like a VHDL process that's running concurrently. Then we have await and start soon. So if you want to await for something to finish before you continue your current coroutine. Use await, for example, if you are resetting the dot or waiting for a bus read or write operation. And then if you want to run the coroutine concurrently and continue the execution of the current one, use start soon. A good example is starting a clock generator in the test bench. You have a bunch of triggers to control your simulation. For example, you can await for a rising or falling edge or for certain numbers of cycle. And there is deep ones that control the simulation cycle, like the read-only or write-only phase. You can also make your own signal state or stability test, like shown here. They're not built in at the moment. Now, the demo objective is to show how you can structure a simulation project with Cocotb and how to use the test runner with Python, the third method to run. And it will be performing AXI light BFM transaction-based tests. And there is also here a concurrent checker because device under test is pulse width modulation, and we write something that checks the pulse width and duration. Before one can look at the simulation, one needs to understand the device under test. So briefly, it has one output pin, which is a pulse width modulation, and it has an AXI light bus interface, and there are 4 registers. An ID, which is a read-only hard-coded value. This allows us to test if everything works and we can read. And then the duty and period is adjustable. They are read and write registers. And there is an extra register that counts the total number of PWM ticks since the time the device was reset. Here is how verification projects with Cocotb could be organized. They don't have to be in separate folders, but that's a convention. The HDL is in one folder, and we have the PWM files. This run all is optional. It's just to show the example of running it with direct scripts. And in the test folder, we have split it into multiple files. It doesn't have to be this way, but this is to simplify it. The package contains some definitions for the register addresses and helper functions. The probe is the concurrent class that can check the PWM duty and period. And then here we separated the test runner, which performs the steps of building and running the tests from the tests themselves. So the tests are separate in this test PWM file. There are in general 4 tests, one reading the ID and one is writing random value to each register that is writable and checking that they match when you read back. One it's reading the number of ticks, and one is checking that the PWM output has the correct duty and period. I think now I will go to a live demo quickly. How much time we still have?
You have 12 minutes.
Okay, that is good. So first, I would like to show the test runner, which is the most important part here, perhaps. So you start by getting a runner from the Cocotb library for your simulator. And this shows how portable it is. If you have a different simulator, then the modification might be only changing this to, for example, Cuesta or Riviera, unless you have custom options. Then you have the build phase, and you can supply a lot of options here to Cocotb. Here we are building the 2 HDL files, and we are setting them to library work. And then the elaboration phase happens when you pass the HDL top level in the build case. So when you do this, then it will elaborate this as the top level. Finally, the run phase, which is .test. And here again, you need to specify the top level and library and the test module name, test PWM, which was well appended for the path here so that it can find it with the Python. We have some build arguments that we can pass. The standard is 2008, and we are linking in the SimBuild library. And we have here plus args for GHDL, which will tell it to produce a wave file called trace.ghw. We can now look at the package. The package has the addresses, it's just imported into the test file to make it more readable. And we have a reset dot function. Here you can see how dot.reset.value is 0. We wait 5 clock cycles, and then we set it to 1, so it's active low reset. And here we have setup simulation, which will, in addition, make a clock and a bus master from the Cocotb bus X4 master. I think that's the main points for this package. For the probe, it's a bit more complicated function. I find it convenient to make these concurrent thing classes so that we can keep track of updating the values. It has two methods, one that counts the PWM ticks and one that will measure the PWM duty and cycle using the simulation time, or sorry, the clock counts here. Here I have a function that will start these methods, which are counting the ticks and measuring PWM. Now the main tests file, this will start actually here. So it will call the test runner. When it calls the test runner, it will be, when it calls the test runner, it will be executing the build steps and loading the simulation. Then Cocotb will pick all these functions that are decorated by @test, and they all must be async def. We have first the test that reads the ID, which is AXI master read operation, and then we have self-checking assertions. We are checking it against the one in the package and printing an error if it doesn't match. The registers test, it will produce random values for the two writable registers, and then it will write them using the AXI bus functional model. It will then read back, and if there is a mismatch in the assertion, it will print an error message. The ticks counter, it will create an object of the probe, and it will start the probe after writing some value, of course here. It will let it run for a while, and then it will read the ticks count from the device under test and assert that it matches the checker of the probe. The PWM, which again will start the probe, but this time it will use the it should use the measuring function. So yeah, the probe dot period and duty should be matching what you read from the AXI BFM, or what you have written, sorry, to the AXI BFM as a random value. The way you run this is that you go into the tests folder and you just call Python and run your test file. I have left a bug here intentionally. So you see here that, well, the test here has failed. And if we look at PWM here, it's not clear that the requirements should the tick be happening when it's a rising edge of PWM or when we complete a cycle. So we don't agree here on the requirements, but a possible fix was also added in this file. And if you fix it, you can get now all the tests passing. Finally, to look at the race.gtk wave. That's how GTK wave would look like, and you can look at the signals. That concludes everything I wanted to present. Please feel free to ask questions.
Thank you very much, Haider. Do we have any questions at all, please, Disha?
Yes, I have posted you.
Okay. Two questions, please, Haider. Question one, what buses are currently supported other than AXI4?
I don't have a list in my mind, but I know that Avalon is supported and simple bus, no, not simple bus. AHB is supported, and then there is also external repository. But you can check that in the Cocotb bus repository.
Okay.
But if you search for this,
we'll make sure that that repository link is shared with people after the meeting. That would be useful. Thank you. As another question for you, Haider. Have you tried to use any encrypted simulation models with Cocotb? For most projects, there's usually external IP which is encrypted, but which commercial simulators such as Viviera, VCS, etc., are able to compile and run.
Yes, I have done that actually, not with GHDL, obviously, as this is only shared with commercial simulators. But we have purchased Riviera Pro, and when you synthesize, you get something called the RTL netlist. And I have tried to copy the encrypted thing for Vivado IP cores and compile them, and they are running fine in Riviera, I could say. But I would expect, I would expect any simulator that supports them to work with Cocotb.
Okay. And how would you do non-blocking assignments in Cocotb?
You would do non-blocking assignments, so kind of like Verilog. Well, perhaps, I'm not sure, maybe, Philip can explain better, but if you use the start soon, then it doesn't block the simulation time.
Okay.
In that regard.
Okay, maybe Philip could take up that question as well.
Yes.
So that's on non-blocking assignments, please, Philip, if you're listening.
So,
does the runner call the make file inside the Cocotb installation, please?
You'd like, sorry, can you repeat the question?
Does the runner call the make files inside the Cocotb installation?
The Python runner, I don't think so.
Do you understand the question?
Yes, I think the makefile itself, so the makefile method calls other makefiles that you include. Again, the details are in the presentation I linked, and Philip is more familiar. However, I think the Python doesn't do that runner.
Okay. And how many VIPs does Cocotb have? Can we use it for verification of avionic projects, for example?
Verification IPs.
Yes, I know they're on avionics, so maybe we want some typical avionics IPs. I'm not familiar with avionics IPs, but
yeah, I am not familiar either, but I think that well, again, I'm not the best one to answer this, but the library is still growing. It's still newer than other verification methodologies.
Okay. And the last one is on PyUVM. Has anyone started using PyUVM?
I haven't used it myself. I've heard some people used it, but there is a very good book by the creator of it.
Okay.
And then there's UVMPy, which is trying to be more faithful.
Okay. PyUVM and UVMPy. Okay, we'll look at that.
PyUVM tries to do it in a Pythonic way. This thesis I linked there in the disadvantages is actually very good and thorough. It shows in details the differences and similarities and what PyUVM is lacking, like this register abstraction layer and so on.
Okay. Yeah, all the questions. So thank you very much.
Yeah, you're
Thank you very
welcome.
much. We'll go to the next speaker, please. Thank you.